Just west of the modern city of Flagstaff, Arizona, a dense forest of ponderosa pines stretches toward the horizon under a vast obsidian sky. Enshrined within a domed observatory atop a modest mesa, a solitary figure works late into the night. The year is 1909. The man is Percival Lowell, a wealthy American businessman turned astronomer, and he is obsessed with the red planet. Lowell's observatory, perched on what we now call Mars Hill, houses a state-of-the-art 24-inch refracting telescope. Situated more than 2,000 meters above sea level, it was the first observatory in the world purposefully built at a high altitude to escape the distorting effects of the Earth's lower atmosphere. Through this lens, Lowell sees the heavens with a clarity few of his contemporaries can match. As he sits in his observing chair, notebook in hand, Lowell gazes at a world he believes is teeming with life. In this era before space probes or high-resolution photography, Lowell perceives a Martian landscape crisscrossed by a network of great waterways, singular and double lines stretching thousands of kilometers. He calls them canals. He sees oases where these channels meet, vast reservoirs of water, and he notes patches of green vegetation that seem to bloom and fade with the Martian seasons. To Lowell, this is not a natural phenomenon. He concludes that these are the engineering feats of an advanced, intelligent civilization. He imagines a dying race on a drying planet, desperately pumping water from the polar ice caps to their thirsty cities at the equator. It was a romantic, tragic, and evocative vision that captured the public imagination and inspired the likes of H.G. Wells. But Lowell was alone in his certainty. Other scientists using similar equipment saw only shadows and dust. Was Lowell seeing the secrets of another world, or was he blinded by his own desires? The mystery of Lowell's canals remained unsolved for nearly 70 years. The answer finally arrived in the 1960s, carried by a new generation of explorers, NASA's robotic Mariner missions. As these unmanned probes swung into orbit around Mars, they beamed back the first close-up images of the Martian surface. The reality was a crushing blow to Lowell's dreams. The images were grainy and gray, revealing a rugged, crater-scarred desert. There were no canals, no oases, and no grand civil engineering projects. Mars was a silent, frozen tomb. However, as the Mariner missions were deconstructing our myths about Mars, another mission was providing a transformative perspective on our own home. In December 1972, the crew of Apollo 17 was hurtling toward the moon for the final landing of the space race. Looking back at their departure point, one of the astronauts captured an image that would change human consciousness forever: the blue marble. This photograph showed Earth as an isolated jewel in the blackness of space, adorned with delicate swirls of white clouds and brilliant ice caps. Our world was spectacularly, undeniably blue. Compared to the rusted, dusty remains of Mars, Earth appeared as a lush ocean world, brimming with water. But this contrast raises a fundamental question: why? How did two sister planets, born from the same cloud of gas and dust, end up so differently? To find the answer, we have to investigate the very origin of water itself. Earth is the only planet in our solar system with stable, abundant liquid water on its surface. It defines our world. Approximately 71% of the Earth's surface is covered by oceans, some reaching depths of nearly 11 kilometers in the Mariana Trench. To put that in perspective, there is enough water in our oceans to fill roughly 550 trillion Olympic-sized swimming pools. But water's reach extends far beyond the coastline. It carves sinuous patterns through our continents as rivers and gathers in massive basins as lakes. Below our feet, vast underground aquifers hold fresh groundwater that can penetrate the crust up to 2 kilometers deep. Millions of cubic kilometers more are locked away in the great ice sheets and glaciers of the poles. Even the air we breathe is part of this aquatic system. Water vapor makes up a small but vital portion of our atmosphere, creating the humidity of a tropical night. At high altitudes, it condenses into liquid droplets to form clouds, or freezes into ice crystals before falling back to the surface as snow. Water is the lubricant of our planet. It facilitates plate tectonics by softening the mantle, allowing the Earth's crustal plates to recycle themselves. It has been the primary driver of life for nearly 4 billion years. But the story of how it arrived here is a mystery that is only now being solved by 21st century research. Because according to the laws of physics, the Earth should have been born dry. When the Earth formed 4.54 billion years ago, it did so in a dry zone. The newborn sun was an incredibly violent and energetic star. Its powerful solar winds and intense heat swept the inner parts of the protoplanetary disk clean of lightweight elements, including hydrogen. Hydrogen is the simplest element in the universe, but it makes up 2/3 of every water molecule. Without it, there can be no water. Consequently, the inner planets, Mercury, Venus, Earth, and Mars, were born as barren, rocky spheres. Some scientists suggest that a small amount of water might have been present from the beginning, bound chemically to dust particles that escape the sun's heat. As this dust clumped together to form planetary embryos, this moisture would have been trapped deep inside the rocks of the growing planet. Only after millions of years of volcanic activity and plate tectonics could this internal water be outgassed to the surface. However, most researchers agree that this internal source couldn't possibly account for the 1.3 billion cubic kilometers of water in our oceans today. To find the true source of our seas, we have to look much further out, beyond the snow line, beyond a certain distance from the sun, roughly 4 times the distance from the Earth to the sun. Temperatures were cool enough for hydrogen and oxygen to condense and freeze. Beyond this snow line, the solar system was awash with ice. This frozen water was locked away in comets, giant gas planets, and a vast belt of asteroids. For Earth to get its water, these distant icy bodies had to be moved. The early solar system was a place of total planetary chaos. The giant gas worlds, Jupiter and Saturn, were jostling for position. As Jupiter migrated inward toward the sun and then back out again, a movement known as the Grand Tack, its immense gravity acted like a cosmic sling. Jupiter threw the asteroid belt into a tumult. Millions of icy bodies were ejected from the solar system entirely, but many were flung inward toward the dry, rocky inner planets. When these icy travelers struck the young Earth, the heat of the impact vaporized the ice, turning it into steam that was eventually captured by Earth's gravity. For decades, comets were the prime suspects for this delivery. They are, after all, dirty snowballs made almost entirely of ice. However, recent spacecraft missions, such as the Rosetta mission to Comet 67P, have revealed a forensic problem. The molecular fingerprint of water in comets, specifically the ratio of deuterium to hydrogen, is fundamentally different from the water in Earth's oceans. The match, it turns out, lies with rocky asteroids. Specifically, carbonaceous chondrite asteroids from the outer belt have a molecular signature that perfectly matches Earth's water. These were the primary couriers of our oceans. We have 2 major clues that water arrived late in Earth's formation. The first is found on the face of the moon. Between 4.1 and 3.8 billion years ago, the inner solar system underwent a period of cataclysmic impacts known as the Late Heavy Bombardment. The craters we see on the moon today are the scars from this era. Since the Earth is a much larger target, it would have been struck by thousands of times more debris, much of it water-rich asteroids. The second clue is gold. Elements like gold and platinum are siderophilic, meaning they love iron. During the Earth's formation, when the planet was a molten ball, these heavy metals should have sunk deep into the iron core. Yet our crust contains a surprising amount of gold. This suggests that the gold was delivered after the core had already formed and cooled. Asteroids brought a thin veneer of precious metals and precious water to the surface long after the planet was born. Once the water was delivered, Earth's unique position in the Goldilocks zone took over. We are at just the right distance from the sun, not too hot to boil water away, and not too cold to keep it permanently frozen. Within a narrow window of just 100 degrees Celsius, water can exist as a solid, a liquid, and a gas. As the Earth's crust cooled, the water vapor delivered by asteroids began to condense. The planet became swaddled in a thick blanket of clouds. Then, for the first time in history, it began to rain. This was no ordinary summer shower. This first rainstorm likely lasted for thousands, perhaps even tens of thousands of years. Water hissed and spat as it hit the hot volcanic rock, eventually pooling in the low-lying valleys and craters. Rivers began to carve their way through the landscape, dissolving minerals from the rocks and carrying them into the growing basins. This is why our oceans are salty. The rain literally ate the rocks and concentrated the minerals in the sea. At the poles, the water froze into the first ice caps. In the tropics, the sun evaporated the surface water, fueling a global water cycle that has remained active for nearly 4 billion years. So, if Earth and Mars both received this gift of water from the same asteroid bombardment, why did Mars end up as a desert? Percival Lowell was right about one thing. Mars did suffer a water crisis. Early in its history, Mars was much like Earth. It had a thick atmosphere, a protective magnetic field, and flowing rivers. But Mars had one fatal flaw: its size. Mars is only about half the size of Earth. Because it is smaller, its internal core cooled much faster. When the Martian core stopped swirling, its magnetic field, the shield that protects a planet from the solar wind, disappeared. Without that shield, the relentless stream of particles from the sun stripped away the Martian atmosphere. Without an atmosphere to provide pressure and warmth, the liquid water either evaporated into space or retreated into the ground as ice. Mars was robbed of its water billions of years ago, long before any Martians could have evolved. Earth, however, was large enough to keep its core hot and its magnetic shield strong. We kept our water. We kept our life. As we look back at the blue marble, we realize how much of our existence is due to pure cosmic luck. We are the survivors of a chaotic solar system, living on a world shaped by crashing asteroids and ancient rain. You've been watching the entire history of the Earth. If you enjoyed this journey through time, don't forget to like and subscribe. Let us know what you think about the fate of Mars in the comments below. I'll see you next time.